Alrighty, so we're going to continue here, looking at black body radiation, and it's important to realize that not all objects are perfect emitters of electromagnetic radiation. So we have this coefficient named the emissivity that tells us what the ratio emitted by that object compared to the radiation emitted by a black body at the same temperature would be. So obviously E equal to 1 is going to be a black body. But anything else is going to represent something less, something that's not as perfect of an emitter or absorber. The emission and absorption thing, by the way, they go together. You're just as good of an emitter as you are an absorber. So we have some sample values for emissivity here that you can look at. All right. The main thing that you need to know is that this is the amended Stefan-Boltzmann equation with the emissivity. Okay. An emissivity of 0 is going to imply a perfect reflector. All right, electromagnetic radiation. There we go. That's the formula that you can write down. So an example problem with this, all right, calculate the power per unit area radiated by the Earth at the temperature that we had above if its emissivity is 0.62. So we calculate this new intensity, just the emissivity times the intensity here, 0.62 times 388 watts per meter squared. All right, and we end up with 241 watts per meter squared. So then it says calculate the power emitted by a square kilometer of ocean surface at 10 degrees Celsius if its emissivity is 0.65. So again, power per square kilometer is just going to take some unit juggling to do this here, but the intensity is just going to be equal to the emissivity times the Stefan-Boltzmann constant times the temperature to the fourth power. In this case, temperature is going to be we got to put it in Kelvin, right? So it's going to be 273 plus 10 Celsius, so that'll be 283 Kelvin, all right? And our emissivity is 0.65. So when we do this here, it'll be 0.65 times our Stefan-Boltzmann constant, 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth. And then we're multiply it by 283 Kelvin to the fourth power. When you do all of this, you get 236 watts per meter squared, but the question did ask for per kilometer squared, so we just need to multiply it by 1,000 meters divided by 1 kilometer, and we got to do that twice for both meter units. So it's squaring that conversion factor. What we end up with is 236 times 10 to the 6th power watts per kilometer squared in terms of the intensity of radiation emitted by the ocean, since it does have a temperature. Okay? All right, so another example here. Okay, moving on, talking about our sun now. Okay, so what we want to do is calculate the power of electromagnetic radiation emitted by our sun. If we assume it to be a black body at 5800 Kelvin, I know before I said 6000, you'll see both values used interchangeably. Okay, just stick with whatever they give you. And if we assume it has a mean radius of 7 times 10 to the 8th meters. All right, so what we're looking for is power. Emissivity is equal to 1 since it's a black body, so we can just take this as the following equation. All right, and we have all of our variables that we would need for this, the radius being 7 times 10 to the 8th meters, and the temperature being 5800 Kelvin. Sub in all of our values, and we get the following. 4 times pi times our radius here squared times 5800 to the fourth power. Okay? When you do all this, we get a value of approximately 3.95 times 10 to the 26th watts, and that's how much power our sun emits. Really, it's about 3.9. Okay? We just have the radius and the temperature that are a little bit different. Okay? So our sun is a black body emitter, okay, with a total power of 3.9 times 10 to the 26 watts. So the Earth, we're about 1.5 times 10 to the 11th meters, 1 astronomical unit. We'll talk more about that distance when we get to astrophysics, from the sun. So the question is, all right, how much intensity do we receive from the sun here at Earth? If we assume that the power radiated by the sun is going to be distributed uniformly, all right, we can assume that it spreads out equally and it has like equal influence in all directions, and so we can imagine it spreading out like a sphere, okay, the surface of a sphere. And we could pretend like the sun is at the center of that sphere and that we are located at a distance d, which would be the radius of the sphere. So what we end up receiving here, okay, is if we consider that entire surface area of the sphere for all the power the sun emits to be distributed over, we receive whatever cross-section we are here at Earth, A, as a fraction of that power that's being sent out here, all right? So more specifically, let's figure out what exactly that is, all right? Again, like I said, the Earth is that many meters from the sun. In the sun, we have a radius there, okay? So the idea here, okay, this is the radius of the Earth. The idea here is we want to calculate what the intensity is that we're receiving here, okay? So to do this, all right, at the location of the Earth, we imagine it's emitting equally in all directions. We're going to need this right here to give us the intensity of sunlight that we were receiving on Earth. In other words, at a distance from the sun, the total power is going to be spread over the surface area, okay, of a sphere, an imaginary sphere that has this radius. So to do this, we're going to use that 3.9 times 10 to the 26 watts that we defined before, and our surface area of a sphere with this radius. And what we end up with, approximately, is 1,379 watts per meter squared. Okay? So that is the average intensity of sunlight as it comes to Earth. Now, the question is, how much are we actually receiving on average? Because if you think about it, that's the intensity if we had the Earth cut in half, okay, if it was straight on. But the Earth does not receive radiation straight on. Instead, we receive it over a sphere, the surface of a sphere, okay, approximately that is. So what we can do to get that average, okay, which is what we call the solar constant, is we can just take it as a ratio of that cross-sectional area to the surface area. All right? And that will average for us what the intensity is over this entire area, all right? You know, from this poles where it's 0 all the way to the equator where we're getting this flat on, okay? And so if you look at that, on average, okay, the solar constant, which is what this S is right here, and pardon me, my smart board is freaking out. There we go, okay. It's freaked out a couple times tonight. What we get, all right, is a quarter of the intensity we had in the previous part. So it's approximately, all right, 345 watts per meter squared. This is what we call the solar constant, okay? And this is close enough, right, the 340 there. So that's the idea, okay? That's what we're getting, you know, per day, you know, on the surface of the Earth from the sun. All right. So again, like I said, oh, there we go. It's the same information as before. I think I'm bouncing around here. Whoops, the wrong direction. There we go. So we've shown this, okay? This is what we call the solar constant. Actually, both are called the solar constant, okay? It depends on what they're talking about. If they're talking about the average received on the surface or the you know, solar constant in terms of the flux density being emitted at the distance of the Earth, all right? But we know the Earth, you know, orbits the sun in an ellipse, so this value actually changes. And the range of intensities that we can get are given right here, all right? Yeah, we see this isn't always, you know, the same value. You know, it's continually changing. And so what happens is that this is what ends up coming to the top of the atmosphere. Then the atmosphere, once it gets to the atmosphere, we have a lot of the UV end up being absorbed, as well as a lot of the infrared being absorbed. It's mostly the visible stuff that gets down to the ground, okay? And so what ends up happening is that this number, you know, is much smaller. And the other issue too is, you know, what is the angle that you're at? Depending on what latitude you're at, you could be right here, all right, in terms of receiving your radiation. And so you're receiving an amount, you know, that equals this much area here. It's drawn poorly here, okay? Say we're here, if we're considering that area, but that area is actually only receiving this much. So this area right here is a lot smaller than this area right there, all right? So, all right, this is, you know, pretty much just the information that you're going to need here, all right, for understand the solar constant. The next part we're going to get to, okay, what we're going to do is we're going to build a model, all right, of radiation coming into the Earth and what's being absorbed and what's being emitted. It's going to be our model for how we analyze climate change.